This is the lecture for the first part of Chapter 3, Atoms to Molecules, and specifically it's about calculating the average atomic mass for an element. Now, every element has the same ratio of isotopes no matter where it's found on Earth. For example, carbon comprised mostly of carbon-12, carbon-13, some carbon-14. The percent of each isotope in a sample of carbon, and where you find it, no matter where you find it, is on Earth is the same. How do we know this? Well, we have what's called a mass spectrometer. I'm not going to get into the details of it too much here, but basically you take a sample, and we can use this with larger molecules too. Here we're talking about just atoms. Make it a gas, inject it. Okay, that's what the heating device does. It vaporizes it, makes it a gas, inject it into here. We have an electron beam or some source, some way of ionizing the sample. Basically, this way it knocks electrons off of the atoms. So now they're positively charged. We have two charged metal plates. One's positive, that would be the rear one. One's negative, that would be the forward one up here. What happens is this beam of particles goes through the electron beam. Electrons are knocked off, becomes positively charged. As it goes through the holes in the middle of these metal plates that are charged, because the atoms now have positive electric charges, they're going to be repelled by the first plate as they go through, pushed towards the second plate, and pulled towards the second plate by the negative charge on the second plate. So they're accelerated, and they pass through, some of them anyway, pass through, they're in a beam. So go down the tube in this spectrometer, mass spectrometer, there's a magnetic field, two poles of a magnetic field down here somewhere. And as these charged particles are moving, because they have a charge, an electric charge, and they're moving, they create a magnetic field. And that magnetic field interacts with the magnetic field from the magnet, and the path that these ions are taking is curved. Now, because they're traveling pretty fast, so they go down here. If an ion is lighter, it's going to curve more. And what happens is it will probably, actually it doesn't show it here, but it'll probably hit the wall of the spectrometer or something. It's gone. It interacts with the atoms in the wall. If it's a really massive atom or a more massive atom, it's not going to curve as much. It has more momentum. It doesn't curve as much. Think about a tractor trailer going around a corner and a motorcycle going around the same corner at the same speed. But some of the ions, or at least one of the ions, will go right down the middle and hit a detector. Now the detector is hooked up to a computer which basically counts how many strikes it gets, how many times an ion hits it, and it keeps track of it. What we can do is we can adjust, there's two variables here. We can adjust the strength of the magnetic field, and that's going to affect what mass ion hits the plate, the detector. We can also adjust the strength of the electric fields on these plates, how fast they're accelerated. That's also going to affect it. But let's just keep it simple. Let's say we just adjust the magnetic field. Basically what that means is we know, okay, from the strength of the magnetic field here and the strength of the electric field on these two plates, what mass, it's basically mass to charge ratio, but for us, just what mass element would hit the detector and we would see it. So the computer keeps track of it, and it knows what the mass is on the ions that hit this plate, and then it's sensitive enough to where we can find the mass of separate isotopes of an element, carbon-12, carbon-13, carbon-14, and we can get the relative ratios, the ratio of how many, what percent is carbon-12, what percent is carbon-13, and what percent is carbon-14. That's how we know this stuff. Okay, so for example, okay, carbon-13 and carbon-12, you run it through a spectrometer, and you find that the ratio of the masses is about 1.0836129, that number right there. So what we can say is that the mass of carbon-13 is this number here, 1.0836129 times the the mass of carbon-12. Now remember, or we'll see this later, we define the mass of carbon-12 isotope as being exactly 12 AMU. So that 12, this is the only mass that's an exact number in all this stuff. That's an exact 12. Anyway, that gives us the mass of the isotope carbon-13, 13.003355 atomic mass units. So once we have defined carbon-12 as having exactly 12 AMUs, that's what we define it as, then we could do this kind of experiment and get the relative mass of everything else compared to carbon-12. So because almost every element is comprised of more than one isotope, some are only one, but most of them have more than one, the mass of that sample of that element, carbon or whatever it is going to be a weighted average of the masses of the isotopes. The average atomic mass will be, this is the formula, should memorize it. It says that the average atomic mass of an element is equal to the fraction of the sample that's isotope 1 times the mass of isotope 1. That's the F1 and the M1, plus the fraction of the element that's isotope 2 times its mass, and so on. F2, M2, F3, M3. Okay, so memorize this equation. And so that's what, so each of the F's is the fractional abundance, we call it. Usually what you're given is you're given the mass percent, and the mass percent is just the fractional abundance, or the percent abundance is just the fractional abundance times the 100. So to use this equation, if you're almost always given a percent, you're going to want to divide that by 100 or move the decimal 2 to the left before you use it in this equation. And the masses they're in AMUs here. So again, memorize this equation. Here's how we use it. Basically 2 ways. 3 really. The first one. Okay. Copper, okay, you're told it has 2 naturally occurring isotopes. It's important that you're told how many naturally occurring isotopes it has, because that tells you how many terms are in the average atomic mass equation. In this case, only 2. F1M1 and F2M2. There they are. Okay, so let's do this. So that's the equation that we're going to use. 2 terms in it. All we have to do here is plug in. Oops. That 0.6917 is the percent that was the first isotope divided by 100. So 69.17% becomes 0.06917. The isotopic mass was this. Notice that the fractions add up to 1. They have to do that. And again, as always, keeping track of sig figs. They both terms get 4 sig figs because of the fractional abundances 4. And so we get 63.55 AMUs as the average atomic mass for copper. But the thing is, that's that's going to be on the periodic table anyway. So here's another way we can use the average atomic mass formula. This problem right here. So here, okay, you're told what element it is, which means that when you can find the average atomic mass, the AAM in the equation, by looking at a periodic table. The periodic table that I am using for this problem gives the average atomic mass of nitrogen as being 14.00674 AMUs. So I give you the masses of the two isotopes. I tell you that there's two. You have to know that to know how many terms are on the equation. Nitrogen 14, nitrogen 15. I give you their masses. We want to find the percent abundances of the two isotopes, which means we want to find the F's in the equation, F1 and F2. Once we get those, we'll multiply each by 100 to get the percent. Right, but that's two unknowns. We have one equation, right? So here's what we do. Same equation. But because there are only two isotopes, we know that their fractional abundances must add up to 1. So we can say it like this. That 1's an exact number. So we can solve for either F1 or F2. Let's say we solve for F2. And now we can substitute in the original equation for F2. And it looks like this. Now what we'll do is we'll do the algebra, rearrange it, solve for F2. We know everything else in this equation. We can plug in and get, solve for F1. Plug in and get F1. 1 minus F1 will be F2, right, up here. Once we get the two fractions, multiplied by 100, those are our answers. So let's do the algebra. First, I'll distribute the M2 inside the parentheses. Next, I'll collect like terms. I'll put this over here. Next, I'll get F1 by itself on one side, everything else on the other. Now I'll take this and I'll divide both sides by M1 minus M2. We get our equation. Now I can plug our numbers in. And, when we do the subtraction, we look at places past the decimal. We keep 5 past on top, which ends up giving us 5 sig figs. Negatives cancel, of course. All right, so now we have F1. That's the fractional abundance of the first isotope, nitrogen 14. To get F2, we just take 1 minus F1. And now to get the percents, we multiply each by 100. And that's our answer. We see that nitrogen is 99.632% nitrogen 14 by mass, and by fraction, is 0.368% nitrogen 15, not by mass, by amount.